And now we're going to make a complete change. We're going to go away from calculations. We're going to start talking about how the structure affects the properties of a molecule or formula unit. And in order to understand that, we're going to also need to know some terminology. So this will be about the terminology. We're going to talk about what intraparticle, interparticle forces are, electronegativity, and what bond type is. So we'll start with the types of forces. So we have intraparticle and interparticle forces. Notice that those names sound very, very similar, but there are large differences between them. So intraparticle talks about within the particle itself. Interparticle means it's between two separate particles. What's holding those particles together? To give an analogy, I like to look at the human body. So when we look at the intraparticle forces, we see what's holding the body together. What's holding your arm onto your torso? We have bones, ligaments, muscles, skin. Those types of things are all intraparticle forces. When we look at interparticle forces, again, the analogy is looking at humans. We're going to say, how do I interact with another person? So I might wave at them, I might shake their hand, I might give them a hug, I might give them a kiss. These are different levels, but they're all interparticle forces because I'm doing them with something else. When we look at intraparticle forces, we're talking about forces that hold either atoms or ions together. There are only two that we talk about in this course, and those are your covalent bonds and your ionic bonds. Those are both the intraparticle forces. So you already know about those, although we'll talk more about them later. For the interparticle forces, we have 5 different levels of strength, and we identify them. We're going to talk more about those later on. We identify them by looking at the type of intraparticle force that's present, and then we're going to look a little bit more at something called electronegativity to help us clarify what type of interparticle force is present. What is electronegativity? Electronegativity is defined as the ability of an atom to attract electrons in a bond. What that means is when a bond is formed, they're not always equally shared. So we might have one of them gets more of the electrons and the other one gets less. When we look at a bond, we see the two atoms that are joined together. We'll compare their electronegativity, and whichever one has a higher electronegativity is going to attract the electrons towards itself more. What can we tell about the elements when we look at their electronegativity? Well, we know that elements with low electronegativity values are willing to give up their electrons more, and elements with high electronegativity values are more likely to take those electrons. We know that things with low electronegativity values, if they're willing to give away their electrons, those are going to be more likely to have a positive charge because they're giving away that negative electron. And the elements with high electronegativity values are the ones that like to take in the electrons, and they're more likely to have a negative charge. So you might expect that anything that is likely to become positively charged is likely to have a low electronegativity value. And that's what we see. So generally speaking, metals have low electronegativity values, while nonmetals have higher electronegativity values. Now let's look at the periodic table to give even more detail about how electronegativity changes dependent upon the atom you're looking at. So let's look at electronegativity and periodic table. We know that metals tend to have low electronegativity and nonmetals tend to have high electronegativity. So we already know that, but let's look at then the general trend. That means that everything on the left side of the periodic table has a lower electronegativity than the things on the right, and the general trend is that as we go from left to right, the electronegativity increases. So I know that anytime I'm looking in the same period, that the electronegativity will increase from left to right. So if I look at sodium and I compare it to aluminum, we should see that the aluminum is more electronegative than the sodium. And if I compare aluminum to chlorine, we should see that the chlorine is even more electronegative than the aluminum. So we can go across the periodic table and say that the electronegativity is increasing, with one major exception, and that is the noble gases. So since the noble gases don't generally make bonds at all, we're going to ignore them and assume that they have no electronegativity. Again, we just ignore them. The electronegativity also changes dependent upon how far those electrons are from the nucleus. So we see that as the electrons get further and further away, the nucleus has less of an attractive force for those electrons. What that means is as the atom gets larger, the electronegativity decreases. So as we look in a periodic table, if we look down the columns or groups, we see that within the same group, the larger atoms are going down. That means that the electronegativity at the bottom of the periodic table is less than at the top of the periodic table. So if I ask you which is more electronegative, lithium or cesium, you would tell me that lithium is more electronegative than cesium. We can also look at that and put those two trends together. So going from left to right, we're increasing electronegativity, and going from bottom to top, we're increasing the electronegativity. And that means as we go from the bottom left-hand corner to the top right-hand corner, we are increasing the electronegativity. So we should easily see that francium is less electronegative than fluorine. Remember, we do ignore the noble gases, so the most electronegative element on the periodic table is fluorine. So originally when we learned to classify compounds, we said, does it start with a metal or ammonium? That tells us that it is an ionic compound. This electronegativity is the reason that we follow that. So you already know how to identify something as ionic or covalent dependent upon whether there's a metal present or no metals present. And that's one of the things that we do with electronegativity. The second thing we're going to do is we're going to focus on the section with nonmetals, the covalent bonds, and we're going to look at those to identify which one is more electronegative and less electronegative to see the type of covalent bond that we form. So one of the things I will be asking you to recognize is, of course, which is more electronegative, as we discussed before, but to look at hydrogen. So hydrogen is a nonmetal, and it counts over on the nonmetals. But I want you just to remember, as we go through this, that hydrogen is the least electronegative nonmetal that we have. So as long as you remember that, you don't have to look at any trends for the hydrogen part. Just always remember, no matter what, hydrogen is the least electronegative nonmetal. So let's do some practice with that. Here's a quick you try it to decide which element is more electronegative. Go ahead and pause that video while you answer that, and then when you come back, I'll show you the answers. Okay, let's look at which element is more electronegative in each of the following pairs. So we compare lithium and boron. We look on the periodic table. We see that lithium is to the left of boron. They are in the same row, same period, and so we will know that boron is more electronegative. We look at Sb, which is antimony, and Sn, which is tin. They're right next to each other over here, and we see that the tin is to the left, the antimony is to the right. The ones on the right are more electronegative, so antimony is more electronegative. Now let's look at magnesium versus strontium. We see that magnesium and strontium are in the same group. Magnesium is above strontium, so that means that magnesium is more electronegative. And now let's look at iron and calcium. They are in the same period. Iron is to the right, so iron is more electronegative. And tin and arsenic, so Sn and As, we find them over here, over on the nonmetal end of the world, and we see that they're both metals, but tin is below arsenic, and tin is also to the left of arsenic. And that tells us then that arsenic is more electronegative, because both of them are saying arsenic is more electronegative. And now I have the trick question. So we have aluminum or germanium. Those two are again over kind of in this area in the nonmetal side. We can see that aluminum is above germanium, but it's to the left of germanium. So one case it says it's more electronegative, in the other case it says it's less electronegative. So the answer to this question is it's hard to tell. You would have to actually look at the numbers to see what the difference is. On my exams, on my quizzes, I will not ask you that direction where one's going up and the other one's going to the left. All of the ones that I ask you are going to be in the same direction or either above and below or left and right. So, which one is more electronegative? I can't tell, and neither should you be able to, at least without looking at the chart that tells you the actual numbers. You may see a few questions on Pearson where they ask you those, but they are providing you the numbers so then you can do the calculation. And our last one is hydrogen versus carbon. And this was just to emphasize to you again that hydrogen is always less electronegative than all of the other nonmetals. And so that tells us that carbon is more electronegative. It's known that the difference in electronegativity can determine the bond type. So it'll tell you whether you have an ionic bond or a covalent bond. The problem is, it's all by definition. So I've seen on the internet, some people say a difference of 1.7 makes something ionic versus covalent. Other times I've seen a difference of 2.0. So how do you know which one is correct? Well, in this class, we're not going to worry about it. We're going to generalize it and not focus on any numbers at all. So for us, what we're going to see is that we have an ionic bond if there's a large difference in electronegativity, and we have a covalent bond if there's a small difference in electronegativity. And the way that we're going to define a large difference is if I have a metal with a nonmetal. That would have a large difference in electronegativity because they're going to be on opposite sides of the periodic table. And if we're looking at a covalent bond, those are going to be things with small differences in electronegativity, and we're going to actually focus on those being the nonmetals. We won't see two metals joining together as ions because both metal atoms are willing to give away their electrons and they have nobody to take them. But we do see it on the other hand with nonmetals because both of those nonmetal atoms are willing to take electrons but not willing to give. So the best they can do is to share those electrons. And later in the unit, when we talk about ionic versus covalent bonds and ask which one's stronger, you know that the shared electrons, because they're able to share, is a stronger bond than an ionic bond where one is giving and the other is taking. I like to make a comparison to marriage to understand the covalent versus the ionic bond. In a covalent bond, that says sharing, and so that would be something like being married. When you're married, you share all your money and both of you have a certain amount to put in. It doesn't have to be equal, but they do need to share, so everybody's sharing the money both as income and as outgo, so it's all being shared. And also notice that co is kind of telling us that it's shared because when we say co-op, cooperate, those types of things, that means two things are doing something together. Now an ionic bond is a little bit different. In this case, one is giving and one is taking. And I think of this more like alimony or divorce, right? Not quite as strong a bond. Are you still linked? Absolutely. But in a divorce, one person is going to be giving the money and the other one is going to be taking it if there's alimony. So it just kind of gives you an idea of what the difference is. Are they still linked? Absolutely. But a covalent bond where you're sharing equally and working together is a stronger bond than an ionic bond where one is giving and one is taking. Okay, it's time for another You Try It. So for these, you're going to tell us which type of intraparticle force is present in each of the following compounds. I'll let you know now that there is one trick question in here, and I'll explain it when we get to it. So for the moment, go ahead and pause your video, and when you return, I'll give you the answers. Again, we're going to look at which type of intraparticle force is present. We know that anything with a large difference in electronegativity will be ionic, and of course anything with a small difference in electronegativity is considered covalent. And this is going to follow along with our previous classification where we know if something starts with a metal, it is ionic. If it starts with a nonmetal, it's molecular. So let's begin. We've got KCl. Potassium is a metal, chloride is a nonmetal, and so we know that this is going to have an ionic bond. Here we have CH4, starts with a nonmetal, ends with a nonmetal. That is a covalent bond. We have PF3. Phosphorus and fluorine are both nonmetals. This is a covalent bond. FeS. We have iron, which is a metal, Sulfur, which is a nonmetal, there's a large difference in charge, so we have an ionic bond. Next we have Bri, bromine monoiodide, and that one is two nonmetals, so it is a covalent bond. And next we have AsBr. As is a metal, Br is a nonmetal, that is an ionic compound. And here we have manganese and chromium. Mn is right here in the middle of the transition elements. It's a transition metal. Chromium is over here, and we see that they are both metals. So this one does not exist in our list of choices. And so that was the trick one. And the last one is SO2, both nonmetals, and so we have a covalent compound.